I hope you guys have, logged into like e-class and check out the homework one already. Okay, I have the homework one uploaded to e-class last night. So if you have not done that yet, okay, please do so as soon as possible, because like the due date is the second coming Monday. So if you start early, I think it will help you. Okay, and you need to submit the homework through the e-class system. Okay, the TA is going to set up like an e-class so that you can submit your homework one, okay, through the system, because like there will be like programming assignments in this homework. So if you submit like a paper copy, it will be difficult for the TA to grade it. Okay. So in addition, the term project has been announced yesterday. I also have that announcement like available on the e-class. Okay, in case you didn't show up yesterday. Okay, but it is going to be the Kaggle, one of the Kaggle competitions, the earthquake prediction. Okay, basically I think that type of problem is like important to everyone who comes from like a southeast region of the Asia. Okay, so we experience like the earthquake all the time, right? In Taiwan and like Indonesia. Okay, and so hopefully like doing this type of problems can eventually like be useful to your home country as well. Okay. Anyway, okay, so we last time we talked about the several ways to do the linear equation. We talked about the known equation. We talked about the batch gradient descent. Okay, we talked about stochastic gradient descent. We talked about mini batch gradient descent. Okay, the most important thing is we talk about what is the concept about gradient descent. Okay. Okay. Yeah, I think this dog probably know better about deep learning. Yeah. So anyway, okay. So of course we didn't really talk like the detail about like the mini batch gradient descent, how to implement that. Okay. So now we would like to add a few more words to that. Okay. To sum it up. Okay. So so of course, I mean, you need to be able to feed the data to the training algorithm. Especially for the mini batch gradient descent, because like in the mini batch gradient descent, okay, each mini batch, okay, you could define it, okay, as a fixed size, or you could have it defined like as like a variable size. Okay, so how to do that? Okay, yeah, we're going to explain now. Okay, so so we can modify the previous TensorFlow code. Okay, to do that. Okay, so we need a way to replace x and y at every iteration with the next mini batch. Okay, so simplest way is to do this is to use placeholder node. Okay. So first we need to create a placeholder node. Okay, so these nodes are special because they do not actually perform any computation. They just output the data. You tell them to output at runtime. Okay, so they are typically used to pass the training data to TensorFlow. Okay, during training, if you do not specify value at runtime, it will give you an exception. Okay, so to create a placeholder, so just call the placeholder function. Okay, and we specify output TensorFlow data type. Okay, so you can specify its shape. Okay, I think I already told you guys the shape basically means like the size of your matrix, right? Okay, either the width and height, those type of stuff. Okay, so if you want to enforce it, okay, if you specify none for dimension, it means any size. That is exactly what I'm talking about, because like sometimes you do not know like the size of each mini batch in advance, right? So you like to leave that as like a variable size. Okay, so in that case, you will specify the that dimension as none. Okay, let me show you with this example. Okay, so here, okay, this line we use the placeholder to create a node. Okay, the type of that the data type is float. Okay, and the shape you can see is none 3. First, you know it's like a two-dimensional. Okay, the first dimension is none. It means it's variable size. Okay, the second dimension is 3. Okay, so you can see. Okay, so A is like that. B is A plus 5. Okay, so with TF session, okay, sets. Okay, you define that. You start default session. Okay, you can see. First, I mean, you create, fit dict. Okay, you fit this to A. Okay, you can see. Now A is a 1 times 3 matrix, right? It's a 1 times 3 matrix. Okay, and then you do a B evaluation. Okay, because B equal to A plus 5, right? So you store that result as B val 1. Okay, and then, okay, the next statement, okay, now you assign 4, 5, 6, 7, 8, 9, okay, to A. Okay, that means like A is storing 2 times 3 matrix, right? So you can see that A actually can be used to store either 1 times 3 or 2 times 3 matrix, okay, depending on what data you feed to it. Okay, so it has a variable size for the first dimension. Okay, so after that, okay, you do a B variation again, like the B is A plus 5. So the result is like for every element, you add a 5 to every element, and then you assign the result to B val 2. So then you can print the B val 1 and print B val 2. You can see the B val 1 is like 6, 7, 8 because that's like a 1, 2, 3 plus 5. Okay, each element will be the result of plus 5. Okay, and the B val 2, the print result is going to be 9, 10, 11, and 12, 13, 14. I think that's very easy to understand, right? Right? Okay. So you actually feed the output at any operation of any operations, not just placeholders. Okay. So in this, probably he doesn't like my lecture. Well, okay. He probably thinks I'm too noisy. Okay. Well, never mind. Okay. So anyway, in this case, TensorFlow does not try to evaluate these operations. It uses a value. You feed it. Okay. So that's basically the case. So we can make use of this placeholder to do the mini batch gradient descent. Okay. So we need to change the definition of x and y in the construction phase to make them placeholder nodes. Okay, so x is no longer like a regular node; they become a placeholder node. Okay, by doing that, you can assign the first dimension as a none. Okay, the first dimension is now variable length. Okay, the first dimension, by the way, is like represent like the number of data sets, right? Number of data, number of training data, and you want to use for each batch, right? And so like depending on how big each like mini batch is, okay, you have the right size for that, okay. And similarly, okay, y is like a corresponding like y value, right? So for the same reason, okay, the first dimension of y is going to be none, okay. So originally, I mean, in the batch gradient descent, I mean, this dimension was like n, right? It represents like number of points, right? Okay. Now it's like because we only pick like a subset of nodes, subset of points, okay, as training data. So so this none, okay, basically we replace like the n by, well, like the size of the subset, okay, basically. Okay. Then we define the batch size and compute the total number of batches. Okay. So here we can make the batch size to be a fixed size, 100. Okay. So number of batch is going to be like okay, this n divided by batch size. Okay. Of course, like this may not be, the result may not be an integer. So we need to make it as call a ceiling function to map the result to an integer, okay? And then in the execution phase, fetch the mini batch one by one, okay? Provide the value of x and y through this feed dict parameter, and then evaluate node that depends on either of them, okay? So the code is something like this, okay? So you define a function like this. Fetch batch, okay, you load the data from disk, okay, and then return x batch, y batch. Okay, you can define a function here, okay, and then in the execution phase, okay, you can see this in this like loop for each epoch, okay, for batch index in range n batches, okay, in the number of batches, okay. So x batch, y batch, feed batch, okay, you get that, okay, one batch at a time, one mini batch at a time, sorry. And then you do the training operations, okay, repeatedly, okay, for the number of epochs, okay. And after you finish this for loop, you output the best theta value. That's it, okay? So that's pretty much about it for the mini batch gradient descent code, okay? So which is kind of very similar to the batch gradient descent code, okay? The only few lines that need to be modified are already there, okay? So of course, I mean, after you train a model, okay, you can also save the result so that you don't need to like train it, again and again every time you see the same problem. Okay, so how do you save the model? Okay, you can do that by using the saver node, okay, and the save method. Okay, and you can sometimes training a model sometimes require a lot of steps, okay, and each time you finish one, when I say a step, I'm not saying it's just one single iteration. No. I'm talking about maybe some operations, okay, and you finish these operations. That's considered as end of one step, okay, and at that time you can save whatever you have, okay, for your model, okay. So how to do that? As I said, you use saver node and save method, okay, and that, of course, that will be an intermediate result, right? We call that as a checkpoint, okay. So then you can next time you can just restore whatever you have from the intermediate result, okay, and then continue working on the model, okay. So you can see at the beginning, okay, it's this part is the same, okay, but here it's a little bit different, okay. After you create an initializer node, okay, you create a saver node here. This is a statement to create a saver node, okay. And then in your execution phase, after you do everything to finish the model training, okay, you use the save method, okay, in the saver node, okay, to save this session, okay, and of course you need to specify like the path as well as the name of the file where you want to store your checkpoint, okay. So this is save path, okay, and this file will be used. I mean, in case you want to, I mean, use this model next time, okay. So how to do that? You can restore a model, okay, again by using the saver node and the restore method, okay. So at the beginning of the execution phase, okay, instead of initializing the variable, okay, using the IIT node, okay, now we don't initialize the variables, okay, because when you initialize the node, all the nodes, I mean, they are kind of like you get fresh start. But no, we don't want that. We want to restore back to whatever we have from the previous result, right? So we do this line. Saver dot restore, okay, and we want to restore this session, okay, and we specify the location of this file, okay, and then we can continue working on this model. Okay, so by default, saver saves and restore all variables under their own name. But if you need more control, you can specify which variables to save or restore. Okay, the TensorFlow allows you to have such like a tiny granularity like control. Okay, to like what you want to save, what you want to restore. Okay, but okay, I think most of the time, I mean, save the whole model is probably like the most convenient way. Okay, but here, okay, just in case if you want to do that, okay, this is example. Following saver, save or restore only the theta variable under the name weight. So this one is you just save the theta values, and you use like the name weights, or you just save this one. Okay, not anything else, just the theta values. But most of the time, if you want to continue training a model, okay, you probably want to restore the whole model, okay. If you only restore only the theta values, then that means you need to build another model, okay, and then plug in these weights at the appropriate place, and then continue working on that, right? Okay. In most cases, like I think you still like use the whole model instead of just like a bunch of weights. Okay. So that's pretty much about it for the mini batch. Okay, gradient descent. Okay, so so in the following, we are going to talk about the tensor board, which is a special tool available in the TensorFlow. Okay, it's a visualization tool. Okay, which allows you to see the training process. Okay, and if you examine the training process, sometimes you can get some more insights. Okay, which may help you to have a better tuning for some parameters. Okay, so this visualization tool is called TensorBoard. Okay, So if you feed TensorBoard some training stats, you display, for example, like nice interactive visualizations of the stats in your web browser. Okay, for example, like learning curves. Okay, I will show you a learning curve later. Okay, so we can also provide in a graph definition. Okay, you can actually see like your computation graph. Okay, you display your computation graph like a visual. Okay, so that you can see it very clearly. Okay, I mean the TensorBoard tool. Okay, will do that for you. Okay, so it will give you a great interface to browse through it. Okay, so in case if you have made some mistake in your computation graph, okay, you can also catch those issues. Okay, by visualize the computation graph. Okay, so this is very useful to identify errors in the graph, to find bottlenecks and so on. Okay. So first, what is learning curves? Okay. So one way to look at models generalization performance is learning curves. Okay. So these are plots of the model's performance on the training set and the validation set as a function of the training set size. Okay, so training set size is actually used as an x coordinate, and the y coordinate is like the performance of the model. Okay, you'll see like a learning curve, like example later. Okay, to generate the plots, you need to train the model several times on different sized subsets of the training set. Of course, you need to save those results, okay, in a specific format, so that like when you launch the TensorBoard, okay, it can load the data and display these things like visually. Okay, so before you use TensorBoard, the first thing you need to do, okay, to tweak your program a bit. So it writes the graph definition and some training stats. Okay, for example, like training error. In this case, is MSE. Okay, for our example, okay, to a log directory that TensorBoard will read it, from. Okay, so you need to use different log directory every time you run your program. Otherwise, okay, the TensorBoard will merge all these stats from different runs. Okay, then the visualization will become a mess. Okay, because like all the different runs will be merged into one single visualized like a graph, which really doesn't show anything. Okay, useful. Okay. So the simplest solution for this is to include a timestamp in the log directory. Then, okay, for example, this is an example. From datetime, okay, import datetime. Okay, so now, okay, it's just like you try to get like the time, okay, information, and the root directory, okay, you specify the root directory, and the log directory is going to be composed by the root directory as well as the null. Null basically, I mean, it's like composed of the datetime information. So so pretty much it makes sure that your login directory is going to be different. Okay, so each time you run your code, okay, depending on at what time. When I say what time, I mean like which day, which month, which day, which hour, which minute, which second. Okay, so every time you run it, because you will be running at the model running your code at different time, right? So it will be saved at a different log directory, okay, because the name will be different. Okay. So add the following code at the very end of the construction phase, so that you'll write the information needed by the TensorBoard. Okay. So this is MSE summary. Okay. Equal to this one. Okay. So basically, you record MSE this is like the performance of the model. Okay, the performance of the model. Okay, and you use file writer. Okay, to write this MSC summary. Okay, into this this file. Okay, using like a get this get default graph is like you are going to write the computation graph into the log direction, into the this log file. Okay, and first time I create a node. Okay, blah blah. I think like you get an idea. I will not go into the detail. Okay, and then we need to evaluate this MSC summary. Okay, so here we just create this summary. This is the MSC summary node. Okay, so where do we evaluate that? Okay, here. Okay, you can see every 10 times. Okay, every 10 times you run the mini batch. Okay, because if batch index divided by 10 equal to 0, okay, we are going to do these following steps. Okay, summary string equal to this one. Okay, we're going to store some information. Step equal to epoch times n batch plus batch index. Okay, we're going to record like number of steps we have. Okay, and we're going to write it into the log file. Okay, this information, summary string as well as the number of steps. And then we keep running the session. Okay, so here, okay, you may wonder why don't we record this information for every single iteration. Okay, because here apparently we are recording this information, every 10 iterations, right? We could have done that for each iteration, but if you do that for each iteration, then this training is going to be very, very slow, okay? Because then you are going to do a lot of like recording, a lot of file I/O, right? Okay, so recording this like once every 10 iteration, I think that's going to be at least like good enough. Because remember, we have, if you still remember, how many iterations are we going to do? Okay, we're going to run like 1,000 iterations, right? Okay, if you remember, the number of iteration or number of epoch was defined as 1,000. Okay, so if we store this every 10 iterations, that means we still have like 100 number of points to plot, right? That's pretty much enough for the for the learning curve. Okay. So finally, you want to close the file writer at the end of the program. So you remember to close the file writer. Okay, so that it can. Okay, and when you close the file writer, it is like that point of time is going to really write it into the file. Okay, otherwise, I mean, during before you close the file, okay, it's really writing the content to the memory, okay, to save like the amount of time for I/O, okay, unless like your memory is not big enough to store all the result, then you will write it into the file. Otherwise, you will hold all the intermediate result in the memory to speed up the iterations. So now run this program, you will create a log directory and write an event file in this directory containing both the graph definition and MSC value. Okay. The graph definition is like the graph definition. Yeah, graph definition is here. You get default graph. Okay, this is a graph, your graph definition. And okay. Yeah. So once after you finish running the program, okay, you can open up the shell. Okay, or go to the working directory. Okay. Normally, it's like we assume it's going to be like your home directory, and under the home directory there's a ML, machine learning, okay, directory. Of course, if you specify the TF log at a different place, then well, depending on where you specify it, I mean, it will be a different place. Okay, so ls minus l or TF logs, okay, run start. Okay, so you list the contents of the log directory. Okay, so if you try to do that, okay, you'll see one file. Okay, actually like but if you run it again, the program again, okay, you'll see well, actually this is like not one file. This is actually one directory. Okay, this is second directory. Okay, so under each directory is record all those information in a binary file. Okay. That binary file is readable by the TensorBoard program, but not by human. Okay, because like it's a binary file anyway. Okay. So each time you run it, it will be stored, okay, different. And you can see this one actually specifies the time, okay? So this one means it's 2016, okay? September 6th, okay? It's 9 o'clock. It's 19 minutes, okay? 9:19 and 59 seconds, okay? So this again is it's 9:22, okay, in the morning, and 02 seconds. Okay, so these two are apart for like about less than 3 minutes. Okay, just want you to have an idea. Okay, because we are using like those time information to create a directory, so that the directory name is different each time you run the program. Okay, so this is like you can fire up the TensorBoard server. Okay, then you can visualize the training stats. Okay, so this is how you do it, the TensorBoard. Okay, and you can specify your log directory. Okay, and where that log file is, log directory is. Okay. Then the TensorBoard will read all the file, all the binary file under the log directory. Okay, it will tell you, okay, it's starting the TensorBoard, okay, server on port 6000. Okay, then you can use the browser to navigate to this place. Sorry, not 6000, 6006, port 6006. Okay, so you can use a browser to look at this. To access this visualized result. Okay, it's going to be something like this, and this is going to be the learning curve. So as you can see that, okay, the MSC, okay, was very high, okay, but after a period of time, okay, it reduced dramatically, okay, and keep it to be very low. Okay. And this TensorBoard, okay, is actually has an interactive interface. If you, for example, here, okay, you can actually hit the graph tape, okay. This is very difficult to see, but you can see. I think this is a graph tape, okay. I mean, if you hit that tape, okay, it will display the computation graph, something like this. Okay. So, okay. Then let's stop here, okay, for a few minutes and take a break. And after 10 minutes, let's come back to try to finish this chapter.